So basically, electromagnetic wave. First, the definition, if you want that, what is the definition of the electromagnetic wave? So basically, an electromagnetic wave is having the electrical energy and the magnetic energy oscillating perpendicularly.
Yes, sir. Oscillating perpendicular.
Saying it is very simple. We can say that electric field and magnetic field are perpendicular, oscillating perpendicular to each other. But visualizing this thing and understanding this thing is quite complex. Because, because what is the electromagnetic wave? Just for example, if you will take the example of light. So light is an electromagnetic wave. And what is the speed of light? 3 into 10 to the power 8 meter per second. So speed of light is very, very large. So basically, for the proper understanding of the electromagnetic wave, there is a requirement of relativistic mechanics. So, okay. So in your syllabus, there are some very basic points of electromagnetic wave that you will study. Okay. So we will start accordingly, according to your syllabus. I will start. So basically, this is started from this. All the things are started from the Ampere circuital law. Now see how from the Ampere circuital law.
Yes.
We know Ampere circuital law says that the line integral of magnetic field along a closed path is equal to mu naught times of the current. Mu naught times the current enclosed by the closed path. Okay, so for example, this AB is the wire, and this is a closed loop around this wire. Okay, closed loop, or you can say Amperian loop. So when you will apply the Ampere's law here, Ampere circuital law, so current is like this. So magnetic field will be like this. Suppose the magnetic field at this point is in this direction. This is the magnetic field direction, and there is one dl very small element of this loop, dl vector. I have discussed this in Ampere circuital law. So when you will apply the Ampere and the direction of the B and dl is same, so B dot dl is equal to mu naught I. This is the Ampere circuital law basically. Okay, so what is the use of the Ampere circuital law? Ampere circuital law is used to find the magnetic field. Okay, is used to find the value of the magnetic field at any point. Okay, at any point you can find the value of magnetic field due to any wire, okay, or due to the solenoid, due to toroid, all these things. Okay, so Ampere circuital law is valid everywhere, but there is an inconsistency in Ampere circuital law, and this consistency is founded by a scientist.
Sir, your voice is like cracking.
Okay, just a minute.
Like it's heavy and it's cracking.
Hello, now it's fine.
Yes, sir.
Okay, just a minute. I am just changing one thing. Hello, now it's fine?
Yes, sir, yes. Sir.
Your voice is... Okay, so So this is clear now. After that, there is one inconsistency in Ampere circular law, and that is founded by the Maxwell. So how? Suppose, for example, mm, this plate, okay, is of plate of the capacitor. Okay, so basically this blue color plate is plates of capacitor. Okay, and this capacitor is in the charging condition. Right now, this capacitor is in the charging condition. Okay. So if this capacitor is in charging condition, na, so there will be the current in the capacitor. There will be the current in the wire connected to the capacitor.
Yes, sir.
Fine. So current will be from positive to negative. Current will start from the positive terminal of the battery. Basically, this is a battery connected, and here the charging of the capacitor is taking place. Okay. Now there will be the same amount of current here also, and there will be the same amount of current here also. And what is this? This is a here is complete vacuum. Here is complete vacuum. In between the plates, there is nothing.
Yes, sir.
There is nothing in between the plates. Okay. Now, what you have to do? We will apply the Ampere circular law. Okay, so due to this is a wire.
Yes.
Okay, this is a wire carrying a current I. So this is a wire carrying a current I. So due to this wire, there will be the magnetic field at some point. So I have supposed a loop. I have supposed this is a Amperian loop, or you can say this is a loop. So suppose at this point I am finding the magnetic field. At this point, suppose this is a point X, and at this point I want to find the magnetic field. So what I will do for finding the magnetic field at this point? Okay. So suppose R is the radius of this. Small r is the radius of this loop. This loop has the radius
Small r.
Small r. Okay. So now we will apply the Ampere's law, Ampere circular law, and we will find the value of magnetic field at point X. Okay. So now at point X, we will apply the Ampere circular law says that the line integral of
The close
magnetic
to the
field,
yes, sir.
that is V dot dl, is equal to mu naught times
Mu naught times I.
of the current enclosed by this loop. Current enclosed
Yes.
by this loop is small I.
Yes, sir.
Okay. Now, as this is a circular loop, so at the periphery of this circular loop, the magnetic field will be constant, because from this wire, all point on the periphery or the circumference of this loop have the equal distance. That is why the magnetic field will be constant. Okay.
Yes,
so,
sir.
Okay. At each and every point of this loop, the magnetic field will be. Earlier also we have done this, so we can write this as this is V into dl, V into dl into cos theta. I can write. Okay, this is a dot product, so we can open this dot product V dl cos theta. We can write. Okay, and this is mu naught into I. So basically, suppose the direction of the magnetic field here is in this direction. This is the direction of the magnetic field, and dl vector will be there. So here will be the dl vector also. The direction of the dl vector in the magnetic field are same. So angle between the magnetic field and the dl vector is 0 degree.
Yes.
Okay, so here will be cos 0. Okay, now magnetic field is constant. You can take this out of the integration. So this will be out of the integration. Here will be dl, and this is cos 0, and this is mu naught into I, and cos 0 degree is equal to 1. So basically we will get V into dl. Now closed integral of dl
Earlier also I have told you will be the perimeter of this circle or perimeter of this loop, that is 2 pi r. So you can, and this is equal to mu naught into I. So basically you will get V into 2 pi r is equal to mu naught into I.
Not
So,
I.
so magnetic field at point X, you will get mu naught into
Mu
I
naught
divided
I by 2 pi r.
2 pi r. Basically you are getting some value of magnetic field at this point X. Okay, and after that you have for checking, means how you will check here. This is your calculation, you have done the calculation by the Ampere's law. Ampere's law is saying that, what is Ampere law saying? Ampere's law saying that there is some magnetic field at this point X. Now for confirmation, you have placed a magnetic needle. So basically magnetic needle is a device used to detect the magnetic field. So for detecting the magnetic field at this point F, you have just placed a magnetic needle, and if there is a magnetic field at point X, so magnetic needle will be deflected. Okay, so this magnetic needle is getting deflected. Okay, so at point X, when you are placing the magnetic needle, so here magnetic needle is deflected, means there is some magnetic field at point X, and according to the Ampere's law, there is the magnetic field, so there is no problem till now. Okay, the problem arises when I have taken a loop like this, in between the plates of the capacitor. Now what I have done, I have taken a loop in between
the plates.
plates of the capacitor. Okay, this is your loop 1, and this is your loop 2. And suppose this is a point Y, and which is at a same distance r, small r. Okay, now when you will apply the Ampere circuital law here, at this point Y, so what you will do, same thing you will do. Ampere
Yes.
circuital law means, we'll say that at Y, the line integral of the magnetic field B dot dl is equal to the mu naught times of the current enclosed by the loop. Mu naught times the now can you tell me what is the current enclosed by this loop?
Current enclosed by the loop.
Is there any current
No.
enclosing by? No, zero, means the current enclosed by the loop is equal to 0, and you will find that the magnetic field is equal to 0 at point Y.
Yes.
But now if the no problem, magnetic field is 0. But what then for cross checking, you have just placed the magnetic needle here at point Y, but you found that this magnetic needle is getting deflected. This magnetic needle at point Y is getting deflected. Very strange thing, na?
Yes.
This magnetic needle is deflecting, means if the magnetic needle is deflecting, means there must be a magnetic field at point Y. Okay. But according to the Ampere's law, zero magnetic field. So basically this is the inconsistency of Ampere's circuital law. We cannot apply the Ampere's circuital law here.
Okay.
In between the plates. So here I have written at point X needle deflected, and according to the Ampere's law there is magnetic field at point Y, needle deflected, but according to the Ampere's law the magnetic field is 0 at point Y. So there is inconsistencies Ampere's circuital law. This is proved by Maxwell. Basically this was the experiment done by the scientist Maxwell. Now this Ampere's circuital law is not fully correct. This is not fully correct. So now you will ask me that, you can ask me, sir, there is no current here, then how can you say here will be the magnetic field? This can be the question, this can be the next question. So the answer of this question you will get from the concept of the displacement current. From the concept of the displacement current you will get the answer. So basically what is happening, this is the charge, the capacitor is charging. Okay, the capacitor is charging, and Okay, the capacitor is charging, and okay, so this capacitor is in the charging condition. So in the charging condition means charge on the plates of the capacitor will increase if this capacitor is charging, obviously. So charge on the plates of the capacitor is increasing. Okay. So due to the increase in the charge on the plates of the capacitor, there is an electric field in between the plates of the capacitor. We have
Yes, sir.
discussed.
Yes.
Okay. So charge is increasing. Okay. So here negative charge on this plate is increasing, positive charge on this plate is increasing because this is a parallel plate capacitor. So I have told you in case of the capacitor, the plates have equal and opposite charge. One
Yes,
plate
sir.
is negatively charged, another plate is positively charged.
Positively charged.
So basically, this is the electric field. Electric field you will get in between the plates of the capacitor. Basically, what you are getting, electric field in between the plates of the capacitor.
Yes, sir.
Okay, this is clear. And remember, charge is increasing on the plates of the capacitor. Okay, what is happening?
Okay.
Charge
Charge is increasing on the plates of the capacitor.
And due to this increase in the charge, electric field is increasing. Increasing means you can say if something is increasing, you can say something is changing. Suppose your height is increasing. So what you will say? Your height is changing now?
Yes, sir. Displacement.
If your height is decreasing, means cannot decrease, but just imagine
It
if
is
someone
it is changing. Yeah.
changing. Changing means increasing or decreasing. So basically electric field is changing. Changing electric field, now you can say there is a changing electric field in between the plates of the capacitor. So what you can say? Changing electric field between
Plates of the capacitor.
Plates of
Capacitor. Sir, I'll note this down.
Okay. If you want,
this,
you can take.
Yeah.
You have
No,
already completed this.
No, I have to write this.
Okay, so what you if you want to take the screenshot, then you can take the screenshot. That
No,
will
sir.
save
Actually, if I do this screenshot, I actually forget after that. Like I have to write.
Okay. So, okay, no problem.
Okay.
So basically, changing electric field between the plates of the capacitor.
Yes.
Right.
Displacement current.
And basically, now what happens? Na, here you have asked me that, sir, from where here is some magnetic field at point Y. So basically, that magnetic field, and you will say that, sir, here is no current, and then also here is the magnetic field. So actually, now what happens in real life? In reality, what happens? Due to this change in electric field, na, there is a displacement. There is a magnetic field here. Due to change in electric field, there is a magnetic field. New concept. Okay. And there is a concept of the displacement current. So in between the plates of the capacitor, there is a displacement current, and that displacement current is due to change in electric field. And due to that, there is a electric field at point Y, magnetic field at point Y. Suppose this is a point Y, and there will be the magnetic field here.
Yes, sir.
Okay, there will be the magnetic field. Okay. So at why there is magnetic field? Because of the displacement current, you can say, or you can say displacement current is due to change in electric field. Okay, so here I have written Maxwell said that not only current produces the magnetic field, but a changing electric field in vacuum or free space produces the magnetic field. So basically, this is the thing. Basically, this is the at point Y you will get the magnetic field due to the change in the electric. Now yes. What we can say earlier, what we have said that earlier what the Faraday said changing magnetic field produces the electric field.
Yes, sir.
According to the Faraday's law of electromagnetic induction, Federal law of electromagnetic induction says that if there is a change in the magnetic flux, there will be a induced EMF. Okay, now related with, in another way, we can say if there is a change in magnetic flux means the magnetic field is changing. You can
Yes.
say, and EMF means you can say electric field. EMF is related to somehow electric field. So you can say earlier Faraday said that changing magnetic field can produce the electric field. Changing magnetic field can produce
Can
the
produce the
electric field.
electric field.
Now Maxwell said after that changing electric field can produce the magnetic field. Okay, and he also gives the concept of the displacement current. Okay, so concept of the displacement current is given by the Maxwell. So okay, so now what is displacement current? Now before the displacement current, you should know uh, the current in the wire is known as the conduction current. This current is the
Yes.
conduction current,
Conduction current.
and this the current in between the plates of the capacitor is displacement current.
Displacement current.
Yeah, basically, the conduction current is represented by I suffix C, and here conduction current is represented by I, and displacement current is the current due to changing electric field or electric flux. Okay, electric flux. What is electric flux? Number of electric field lines crossing the plates of the capacitor perpendicularly is the electric flux. Instead of electric field, we will use electric flux to define the electric current. Okay. So you can define the electric displacement current like a current due to changing electric field means changing electric flux also,
Flux, yes,
because
sir.
electric flux is given by EA cos theta.
EA cos theta.
Okay, and the formula given by the Maxwell is epsilon naught d phi by E, d phi E by dt means change in the electric flux, and this is epsilon naught means the absolute permittivity of the free space, and this is the formula for the displacement current. Okay, and this displacement current and the conduction current experimentally found that is same.
Yes.
So at point x and y the magnetic field is same experimentally, so conclusion is that the displacement current and the conduction current are same. Okay, so basically this is a concept given by the Maxwell.
Maxwell.
Now there is a modification done by the Maxwell. So here in wire there is a displacement current in between the plates of the in wire there is a conduction current in between the plates of the capacitor there is displacement current.
Displacement current.
So earlier what is the Ampere circuital law? V dot dl is equal to mu naught I. Now
Mu naught
Ampere
I.
circuital law will change. Ampere circuital law you can write V dot dl is equal to mu naught times of conduction current
I,
plus displacement.
I plus I theta.
And it will become conduction current is I and displacement current you know epsilon naught d
Epsilon d phi E by dt.
and this is known as the Ampere's Maxwell law. And there is one more point for the conductor. For the conductor, the displacement current is zero. Means in conductor or in wire there will be no displacement current. Okay, so displacement current exists in dielectric or insulator. Okay, so now you can note down if you want to note down this. You have
yes.
Actually, na when you note down by yourself, na it gives you a better understanding. I think.
Yes, sir.
Either taking the screenshots or. So now, Harsh, can you tell me what is the inconsistency in Ampere circuital law?
In inconsistency in Ampere circuital law.
Means I'm just asking, what is the inconsistency? Just we have pointed out in the Ampere circuital law.
So displacement current.
No, displacement current is not the inconsistency. Means inconsistency is that when we are applying this Ampere circuital law in between the plates of the
Oh
capacitor.
yeah,
Means
please.
in a dielectric medium when you are applying. So in that case there is no current.
Yes.
So if no current, so it gives the zero magnetic field. But
Yeah,
there is a magnetic
we
field.
put a plate in between the parallel plates.
Yeah.
There will be current and magnetic field will be there.
Yeah. In Viva, the examiner can ask you this question.
Done, second, scroll down. Harsh, tomorrow will you take class? Yes,
Tomorrow?
sir, you can take class.
Fine. So maybe we will finish tomorrow this.
Yes.
But the condition is that you have to write fast. Because,
Yeah.
Mostly in this chapter, from this chapter, the questions appeared in your exam from the electromagnetic spectrum, the last topic of this chapter.
Second, scroll down.
So do you remember the chapter, the wave that you have studied in your 11th class? Wavelength,
Waves.
frequency.
Yeah, in
Wave.
second term I studied.
Actually, those concepts will be used here of waves because we are studying which chapter? Electromagnetic waves.
Sir, but
So
in that also there was so much deleted because of 35 marks paper.
okay, no problem. So that basic things I will be this will be required. So I will first explain that, then we will move. So don't
Yeah,
worry
just
about that.
done, sir.
Done. Okay, very good. So write down this statement also.
Yeah, yeah, yeah.
Maybe tomorrow we can take we can have 2 hours of class if you are means okay.
Yes, sir. Done, sir.
Done. Okay. So this can be asked in your exam. What is displacement? Very important.
Okay. Done, sir.
Done. Okay.
Done, sir.
Done. Okay.
Sir, just hold on.
Hold on.
Done, sir.
Done. Okay. Uh, uh, can you tell me what is the source of electromagnetic wave?
Source.
Means from which thing we can get the electromagnetic wave?
Current.
Of course, if current is changing with time, then we can get. Basically, after that, there are Maxwell equation.
So this is related, right?
Yeah, this is related. So I am just explaining you. Don't write it. Basically,
Yeah.
basically Maxwell equation are the equations, four equations given by Maxwell. First is Gauss law of electrostatics. Okay, close integral of E dot dA is equal to Q in by epsilon naught. And another Maxwell equation, Gauss law of magnetism. Okay,
Yes,
P
sir.
dot dA is equal to 0. This is the Gauss law of magnetism. And another Maxwell equation is Faraday's law of electromagnetic induction. Change in magnetic flux induces the EMF. This is the formula. In another way, you can define the Faraday law. Changing magnetic field induces the electric field, and you can write this like this. And fourth is Ampere's Maxwell law. Okay, B dot dl is equal to mu naught IC plus IT. Okay, so Maxwell equation.
Yes, sir.
Okay, so now we will discuss what the Maxwell said. Recap, we will do the recap. What the Maxwell said? Maxwell said that a changing electric field can produce the magnetic field. What Faraday said? Faraday says a changing magnetic field can produce the electric field. So this is the recap. Faraday said a changing magnetic field induces an electric field.
Electric field.
Maxwell said a changing
A
electric
changing
field
electric field
induces a magnetic field.
magnetic
But
field.
this statement is very important. Induced electric field by the magnetic field
Is perpendicular to magnetic field.
and induced magnetic field by the electric field is perpendicular to electric field. This is so just copy this fast.
Okay, just a minute.
Then we will discuss what is the source of the electromagnetic wave.
Done, sir.
Done. Okay. So now we will discuss a source. What is the source of electromagnetic wave? Is a accelerating charge. If a charge is moving, if there is a motion of the charge, we know there is a electric current due to that charge. A moving charge produces the electric.
Yes, sir.
A moving charge produces the current, and we also know that a
Yes.
moving charge produces the magnetic field also. And
Yes.
if that charge is moving with some acceleration, means the velocity of that charge is changing with time, then we will get a changing magnetic field and changing electric field from that charge, and that is responsible for the production of electromagnetic wave or generation of electromagnetic wave. So source of electromagnetic wave are accelerating or oscillating charge. Okay, an accelerating or oscillating charge. So this is suppose a charge, and this charge, this charge, what happened? Okay, source of electromagnetic. So basically this is a charge, and this charge is accelerating. What is the meaning of accelerating? Moving with variable velocity. Moving with variable velocity. So due to the motion of the charge, there will be the current. Okay, due to the motion of the charge, there will be the current.
Yes, sir.
And due to the acceleration, this current is changing, and due to change in the current, there will be a change in the magnetic field, and due to that change in the magnetic field, there will be the perpendicular electric field. And basically in electromagnetic wave, there is electric field and magnetic field oscillating perpendicular to each other. So accelerating or oscillating charge is the source of the electromagnetic wave, and from where we get the oscillating or accelerating charge? From the LC circuit. LC circuit means when you will connect a capacitor and a inductor in series, then from this type of circuit, and suppose this
Yes, sir.
capacitor is charged, okay, then what will happen? There will be the discharging of the capacitor. Okay, basically this is the LC oscillation, and LC oscillations removed from your syllabus, so you can just write like this only. So from the LC oscillation, due to LC oscillation, we get the oscillating charge. we get oscillating charge. And oscillating charge, if something is oscillating, means accelerating.
Yes, sir.
And due to accelerating charge, we get the time varying magnetic field, and electric field. And these are perpendicular. These are perpendicular to each other.
Yes,
What
sir.
is what perpendicular means? Magnetic field. And
Magnetic.
just write down fast. LC oscillation means in a LC circuit there is an oscillation of the charge basically. I am not
Yes, sir.
explaining how there will be the oscillation. You should just remember the thing. Basically, this is the inductor and this is the capacitor. And this capacitor this time is fully charged. And so what we can say, an accelerating charge particle can produce the electromagnetic wave.
Yes. Second school.
Yeah. Basically, this is a LC circuit.
Yes,
Okay,
sir.
so you can write an oscillating charge, an oscillating or accelerating charge produces EMW, electromagnetic wave.
Yes, sir.
So after that we will see. Actually, time is up now. I am having another class.
Okay. Done,
at
sir.
9. Done. Okay.
Yes.
So basically, I want to show you what is the graphical representation of the electromagnetic wave.
I saw this in the book guide also.
Yeah. So basically, in this description or in this graphical representation, I have assumed that the electric field is oscillating along the y-axis. This is the y-axis, and the magnetic field is oscillating along the z-axis. And
Yes, sir.
the direction of the propagation of the wave means this energy is transferring, or you can say energy is moving towards the x-axis, means direction of the propagation. So I cap is representing x-axis, j cap is representing what is j cap? J cap is the unit vector in the direction of the y-axis. Now you can see
Yes,
here, what is happening here. For the electric field, first we will see what is happening with the electric field. Okay. Now at this point, electric field is 0.
Yes, sir.
Now when this energy is moved, or after that what you are watching here, this arrow is representing the value of electric field. So now see, here is some value of electric field. Next arrow is bigger than the previous one.
Yes,
what
sir.
is the meaning? Means electric field is increasing.
Another
arrow now means from here to this point,
it increases.
Yeah, electric field is increases from here to this point. Yeah, okay, that thing we will, I am not going in that. Basically, from here to here, the electric field is increasing.
Yes, sir.
Now, from here to here, the electric
Decreasing.
field is decreasing and becomes zero.
Yes.
Okay, now after that, what is happening? From here to here, now, and you have to see the direction of the arrow at the same time. See, the direction of the arrow is along positive y-axis.
Yes.
And now from here to here, the
Negative
electric field is
y-axis.
increasing. Electric field
Yeah.
is increasing, but in negative direction.
Negative direction.
Means the electric field has changes the direction now. Okay. Now here the electric field becomes maximum.
Yes.
Here
Sir.
the value of the electric field is maximum. Now from here also the electric field is decreased to zero in a negative direction from here to here. And again from here to here the electric field is increasing in a positive direction. And from here to here again the electric field is decreasing and becomes zero.
Zero.
And from here to here the electric field is increasing in the negative direction and becomes maximum. And from here to here the electric field is decreases and becomes to zero in the negative direction. So basically what is happening with the electric field? What is happening with the electric field? Suppose this is a mean point,
Yes,
and
sir.
first this direction is positive and this direction is suppose negative. Okay, this direction is positive, this direction. What is happening with the electric field? Electric field is first increasing in the positive direction and
Yes.
becomes maximum. Now again after that electric field is increased and becomes maximum. After that what happens? Electric field is decreased and becomes zero. Means from here to here becomes zero. And after that what is happening? The electric field is again increasing in the negative direction and again becomes maximum. Okay.
Yes, sir.
Here to here the electric field is increasing and this electric field is now, see the direction, is increasing in negative direction and becomes maximum. After becoming maximum it is decreasing and becomes zero. So basically this thing is known as the oscillation. The electric field is zero, maximum, again zero, maximum in negative direction, again zero. So this is known as the oscillation of the electric field. So basically
Yes, sir.
this oscillation of the electric field is taking place along the y direction. Same is the case with the magnetic field along the z direction. And remember that, see, this electric field arrow and the magnetic field arrow are perpendicular. So you can say the electric field oscillation and the magnetic field oscillation are perpendicular to each
To
other.
each other. Yes, sir.
And one more important thing here, the electric field and the magnetic field are also perpendicular to the direction of the propagation of the field.
Progression of wave. Yes, sir.
Okay. So
Yes.
basically here you can say few points I will write. Here you can say electric field, it is written that electric field is along x-axis. So I am writing this electric field oscillating along which axis? Y-axis. Okay. And magnetic field oscillating along z-axis. And can you tell me what is the direction of the propagation?
Direct x-axis, right?
Yeah, direction of the propagation of wave, electromagnetic wave along x-axis. Now can you tell me x-axis, y-axis and z-axis are mutually perpendicular? So basically if electric field oscillation, magnetic field oscillation and direction of the propagation are mutually perpendicular, this is representing the transverse nature of electromagnetic wave. Transverse nature
Of electromagnetic waves.
Transverse means the direction of the propagation and the direction of the oscillation when becomes perpendicular. That wave is that wave having the nature of transverse nature.
Yes, sir.
And one more point here, you have to remember that electric field and magnetic field are in same phase.
Same phase.
So what is the phase? Basically, now you can see at this point, what is the meaning of the phase? I want to tell you. Okay. So basically, phase is just here at this point. The
Yes,
electric
sir.
field is 0 and magnetic field is also 0.
Yes.
Now see here at 90 degree. This is basically a 90-degree position. Okay. This is a position. 90 degree means this is the position half of the T/4 of the time period. So basically here at this point the electric field is maximum and magnetic field is also maximum. Now at this point electric field is 0 and magnetic field
The
is 0.
magnetic field is also 0.
So this is the meaning of the same phase.
Yes, sir.
At the same time the value of the electric field and magnetic field is same
Yes.
at different interval of time. So okay, so now what you have to do, can you draw this or it is better to take the screenshot? I think
Sir, I took the screenshot.
I don't think you can just draw this.
I mean,
Okay, so
yeah,
but write down these things.
I wrote
These
that.
things are this also.
Yeah, or the yellow and the green part I wrote.
Okay, so this is the transverse nature of the electromagnetic wave.
Yes.
So basically, what is there you have to remember, and don't say that in any book or in any other exam in your CBSE 2023 exam, you can get the electric field oscillating along z-axis also.
Yeah.
Okay, this is not mandatory because we are choosing the axis.
Yes,
Okay.
sir.
So the electromagnetic wave is an electromagnetic wave. Suppose electromagnetic wave is traveling like this in this region. So that is I am the observer. I will choose the axis. So I suppose any one person is choosing this axis, means this coordinate axis system.
Yes, sir.
Another person can choose the in this direction z direction and in this direction y direction. So don't think that always the electromagnetic wave always in electromagnetic wave the electric field will be along y axis, always along the z axis, always the direction of the propagation will be along x axis. It can be z axis also. Direction of propagation will be z axis also. Okay, you will get
Yes, sir.
you will get it with time. Okay, so please write down the heading also. This is a graphical representation and this is very most important part. Means you should know how the electric field and the magnetic field is behaving.
Sir, I wrote that. Done.
Oscillation means first increasing, then decreasing,
Then
then becomes
decreasing.
0,
0.
increasing in
Then
negative,
again increasing.
then
Then
again
decreasing, becomes
increasing.
0.
This is the meaning of the oscillation of the electric field and the magnetic field.
Yes.
And what is electric field and magnetic field? Energies.
Yes,
Electric field
sir.
and magnetic field are simply the electrical energy, and basically in electromagnetic wave, in simple word you can say there is a oscillation of the electrical energy and the magnetic energy, but the oscillations are taking perpendicular to each other as well as the perpendicular to the direction of the propagation. And remember that electric field and the magnetic field in the electromagnetic wave are in same phase.
Yes, sir.
Okay, now if you want, then you can leave the class. Okay, so tomorrow,
Okay, sir.
if you will join, then tomorrow we will discuss some more interesting things. Okay.
Yes, sir. Yes, sir. Tomorrow I'll
And
join.
tomorrow, definitely we will finish this